Welcome back to another episode of Freeform AI. My name is Michael, and I do data engineering and machine learning at Databricks. I'm joined by my co-host. His name is
Wilson. I take messy and confusing documents and I try to apply semantic distillation to seek truth at Databricks.
Today we're speaking with Deanna. Deanna studied physics at Harvard and then data science at Berkeley. And then in industry, she took a variety of roles. First, she worked at Aon, quickly becoming a principal. And then 2 years ago, she joined Quotient AI as the founding AI researcher. And a few months ago, Quotient AI got acquired by Databricks. And so Deanna joined our team, and we've had the privilege to work with her pretty closely. So Deanna, just kicking it off in a light, fun way, you worked at the Harvard and Smithsonian Center for Astrophysics. What the hell does that mean?
Well, thanks guys for having me. Yeah, so the Smithsonian Center for Astrophysics is basically a group of researchers at Harvard that are also connected to like the federal research component. So they have like, if you know, well, you probably don't know, there are some big satellite telescopes like Chandra, and those are managed by Harvard researchers, but it is a federally funded research project. And so I got to work with the scientists there, which was really cool.
Okay. Can you define astrophysics for me?
I guess broadly speaking, it is any research that pushes the boundaries and like our understanding and knowledge of the universe outside of the Earth. But that can involve research that is in the Earth. Like, I don't know, so much of atmospheric research is also astronomy, astrophysics. But broadly speaking, study of the universe.
Okay,
Okay.
that's
Hot
pretty
take.
cool.
What's your favorite photon wavelength band?
Man, hot take.
Yeah.
I think maybe the hot take is X-ray wavelength.
Nice.
X-ray wavelength, there's a lot of high energy activity happening in the universe, and you can get to observe it through the X-rays, and it's really cool.
Yeah, who doesn't love a pulsar and who doesn't love supernova, right?
Right? Exactly.
So while going through and working on that, coming from a physics background, what excited you most about being exposed to that sort of data and working with the teams? Was it the discovery of stuff, or was it applying what you've learned to do with data science in like applying to that?
I think it was definitely the application. I really enjoyed getting a super messy image. Like you'd get essentially a satellite captured image of a whole bunch of pixels with different photon counts effectively. And some of that is noise from satellites. Some of that is noise from just like general emission in the universe. And you're trying to understand something about this particular object in that image. And you have to go through so many filtration steps, cleaning steps. And that was really what excited me. How do I take this messy, noisy thing and turn it into a real takeaway and understanding of the object I'm trying to study?
Yeah, it was something that when I did electives on astrophysics in college, because I've always been like a space nerd, and I probably know less than 2% what you know about all this stuff. But it blew my mind the first time that I understood that the data coming from space-based telescopes and even some of the stuff that comes from like ground-based stuff, like exactly as you just said, it's photon count and like frequency of that photon that it was measured at in order to like create an image. It's just basically a bunch of digital information that a bunch of really smart people have to be like, we need to make some calls here on like, how do we interpret this? And then what are these different wavelengths from emission spectrums? What would that actually do to render like a color picture? And a lot of people just see the pictures out there and they're like, that's so pretty. And like, you have no idea how much work went into that one image.
I mean, not to mention, like, the colors are actually not real. They're just representations of the different frequencies of light. But it is super cool how much information you can get from just that photon count and wavelength. You can If you go off of theory and you have some understanding of how something behaves, then you can say, okay, well, I know that this thing should behave in this way, but I'm seeing it in this frequency, and I can turn that into a way of measuring velocities of objects. And it's really cool how much you can get out of so little information.
Was there ever a point where your team was collecting data that you're looking at some sort of redshift data and you're like, is this real? Or look at it and be like, this is so cool that somebody theorized that this would happen, and now I have direct evidence of this.
Absolutely.
That's got to be like a mind-blowing event where you're just like, this is awesome.
Yeah. I think one of the projects I worked on that I really enjoyed the most was it was also an X-ray wavelength, and I was looking at two colliding galaxy clusters. And so those are just like every single dot that I saw in this image was a galaxy. It wasn't a star. And that's really cool that you can look at things at such massive scales that are so, so far away in space that it's just, I don't know, makes you feel very small.
What did you focus on for your thesis?
So I think my sign that I was going to leave astrophysics was that I didn't focus. I just kept jumping from, I don't know, I did some things in X-ray wavelengths at the like galaxy cluster scale. Then I did brown dwarfs, and like a statistical survey of X-ray emissions from brown dwarfs, which is an unexpected thing because brown dwarfs are supposed to be cold stars, low energy. And then my senior thesis was looking at maser emission in the radio wavelengths around, like from the disk around a star. So I kind of did a bunch of random things.
Okay, cool. And then you moved into data science. Was
Yes.
this a logical step because you've done so much stats and ML via astrophysics, or was this more of an intentional transition?
It was more of a logical step. I think I wouldn't say that I had done a lot of ML. All of my coding skills at that point were really just scrappy, whatever I need to do to get this job done. So transitioning into data science was just an application of like, oh, I like to solve problems with messy data and learn something about the world around me. And so that made sense and learned as I went along, I guess.
That's very cool. Yeah, go ahead, Ben.
But I mean, you're not the first person that I've met that's gone into a subdomain like super deep in ML or like in AI as a blanket term, who comes from a discipline that requires a level of systems thinking that dwarfs what most people actually experience in a professional capacity. When you're looking at something like per pixel photon levels and wavelength readings from an image, and you're chunking through terabytes of data feed in order to create something that is meaningful for research, you're not doing first order thinking. You're doing like third, fourth, fifth order thinking of like, what could this actually be and what causes this and what is around that? And so that level of kind of deep associative reasoning, do you think that that is what eventually drove you to arguably the most complex part of Gen AI right now, which is effective evaluations?
Yeah, I think whether it was intentional or not is a separate question, but I think it just kind of naturally progressed in that direction. I do feel like evals in general is, to me, it is the core of AI. Like training models is evals. Training, whether it's AI, ML, it's all evals. And so evals feels like, I don't know. I don't know how there's AI without evals, I guess, or how there's ML without evals. So it was just the interesting thing for me at the time and still is.
Can you define what excites you so much about problem solving? So, like going into your head a little bit, it seems like you've worked on some of the hardest stuff in some very prestigious locations. So, when you're thinking through a problem, what is that like? What is the exciting aspect about it?
I guess part of the exciting aspect is becoming a SME, getting to know the data and all of the edge cases so well that you can, I don't know, like in industry, that you can find weird scenarios and flag them to like someone who is an expert and be like, hey, I saw this. What does this mean? And that stumps them. That's really exciting to me. I like understanding the chaos in the world. I like identifying chaos, understanding it, and then trying to make sense of it.
That, yeah, that makes a lot of sense for studying the theory of the world. I'm actually curious, Ben, what is when you're solving a problem, what is the emotional driver for you these days?
You just took my thunder. I was going to ask something similar to Deanna. We'll get to my question in a minute, but or we can just go with my question. We can both answer it. What is your reasoning chain with respect to there's modes of thinking and philosophies of thought, which are there's a linear stage of thought process that you go, almost like a hierarchical, stage of I'm going to ask this question, get an answer, ask another question, get an answer, and compare that to intuitive thinking, which is almost subconscious pattern matching with regards to arriving at an answer. I'm curious, which of those two schools do you feel that like you kind of sit in a little bit better?
Hmm. I think I probably, well, maybe just to take a step back to like restate the two schools that you see are one, or maybe, sorry, can you restate what those two schools were to you?
Yeah, like the first one is more like almost a prescriptive declarative thinking process where you're going through a checklist almost of I see this bit of data or this aspect of entropy. I need to ask my first question and then I answer that, and then that opens up two additional questions. I need to go and then come up with answers to that versus almost I wouldn't call it chaotic, but more like an intuitive reasoning chain where you're like, I'm going to explore this problem, look at the chaos and noise, collect as many data points as I can in my head right now. And then my brain just kind of starts drawing almost like a graph of possibilities in order to arrive at an answer.
I feel like it's, well, for me, it's hard to have one without the other, maybe, which is not a
Interesting.
direct answer, but I like to have, I mean, every problem is different, but when you're just starting and trying to understand and grasp whatever domain space is, there is maybe a process that you can start following. But then as you follow that process, you identify things that like you start to go down rabbit holes. And that's where the chaos begins and where you start to like get a whole bunch of different data points and then try to understand and put them together, grasp, like identify patterns, and then come back up the rabbit hole and go down another one kind of thing. At least that's how I see it. But maybe it's a bit of both, but maybe it's mostly the chaos. I don't know. That's not a good answer.
I think it's a perfect answer. It's more like, I mean, what that reads to me is by default, you're probably in the second group, but you're applying scientific rigor to it,
That might
which is,
be.
I think, some of the most effective thinkers out there are somebody that's like, I can use intuition, but I'm going to structure it in such a way that I'm setting aside a bunch of hypotheses and then either validating or invalidating each of those in order to build a more effective model of the state of the world. I'm curious, Michael, which are you of those two polar opposites?
I agree with Diana. I see them as tools in a toolkit where the first provides structure and then the second is sort of the engine. So I think they're sort of the same thing. But I think at the most extreme, you're thinking about free association and like, well, this is the answer. It's 42, obviously. And then the other one is like creating like axioms in a mathematical proof where there's very clear sequential deductive steps. And to me, that the glue between each step has to be that freeform association. Like you can't reason, like the jump between 2 points is the freeform reasoning. But that's my 2 cents. What's your thoughts?
I mean, I've like personally met people that are in all three of those groups. Like definitely have worked with people Databricks R&D where you sit down in a meeting with somebody and they are fully in that like that extreme case of they just intuitively know maybe they can't articulate why, but they come up with a conjecture, and then you spend 5 days working on the problem and it turns out that every single detail of what they intuitively understood about the problem was correct. It's like a map of reality that they just know. And you're like, how does this person exactly do this? And I've also, not in this profession, but in previous jobs that I've had in different industries, I met a lot of the linear thinkers. They're like, hey, I can process through a list of questions and answers sequentially. Might not be the fastest way of going about it, but they can arrive at some approximation of localized truth through doing that. But I found that most people that are in tech, particularly people that come from like research backgrounds, are more like a mix of the two, maybe leaning a little bit more on the intuitive side. I've always just been curious about like how people's own self-perception of that is. Like, do you see yourself as like a graph modeling thinker, or like what mix that is?
Where do you see yourself?
I have no idea. Just pure chaos. Absolute chaos. I think over the years, I've applied more of, or attempted to apply more of the rigor to it. But a lot of the gut instinct type stuff that I have, I still rely on that pretty heavily for like, this is the shape of how I think this should be, and then just build it and then fix it as I discover that it's broken. It's always broken, but it's just like, maybe it would serve me better if I did a little bit more of the structured thinking while going through that. But I usually rely on intuition.
That's super interesting. Yeah, Deanna, I'm curious your thoughts. What are your, and this is going to sound oddly loaded, but what are your strengths as a AI practitioner? And like, how do you think your approaching or your approach to problem solving and implementation might differ from others in a potentially good way?
Hmm. I think, well, just because I am so data minded, I always want to get my hands dirty and look at like what is the output? How did it come to that conclusion? And so I think going through and looking for all of the weird edge cases of, I don't know, here is a strange response I got from this AI product or tool. And why did that happen? And how often does it happen? Like those really lend well to building. Like AI is just so, it feels random. It feels like you can work towards something for hours at a time, change words in your prompt, whatever, and it still just does not behave the way you want it to, and you don't know how to make it. And so looking at the data is, I think, maybe one of the best ways to get a sense of like, okay, well, I know that there's this one particular thing that's not behaving the way I want, but if I look in a larger scale, is there some kind of a pattern that I can identify that would help address that singular problem in a way that I don't expect, for example? And so thinking about the data, getting your hands dirty in the data, and then also through time spent with data, becoming a SME to an extent in that particular domain that you're applying AI towards, I think are maybe what my strengths are.
That makes a ton of sense. And I've always found this a very challenging thing to communicate of look at the data. Like
Yeah.
when you instruct someone to just like look at the data, build a graph, look at a distribution, they do that, but then gleaning insights from those, I think actually requires a lot of intuition. And as you said, like familiarity with common data structures, data distributions. I remember when I first graduated from university, I would look at a normal distribution or a tail of something and just see a pretty curve. But now I see it and I like have a visceral emotional reaction via a variety of experiences. Like tails are such a cool part of a distribution, and there's so much challenge in that area of a distribution and also opportunity. So if people were going to go and learn some of this intuition, or ideally fast track what look at the data means, how would you recommend they do that?
Man, I don't know if there is a fast track. I feel like looking at the data is just the slowest it gets, but if you take that time and you look at the data, you spend however many hours familiarizing yourself with all of, I don't know, maybe part of looking at the data is understanding your own user's behavior. Part of it is understanding AI behavior. Part of it, like, there's just so much to glean from that, that once you've put in the investment and the time, then you're at the fast track point. Then you can start to build faster and you can understand what you're doing and understand what your failure cases might look like. And that helps you iterate more quickly. But I don't know if there's any getting around it.
Do you think there's any getting around it?
No, like where I came up learning data science was from I guess you could say it was like a weak parallel of what Deanna went through with looking at astrophysics data. Large scale semiconductor manufacturing. We were processing, 800 terabytes a day of like compressed data for just like tool signals in the factory. And if you're just out there looking for a correlation, super simple. Like you could find problems with anything. You could cherry pick whatever you wanted and get a rock solid analysis if you had like zero ethics. But if you actually need to understand like what is the actual causality here, you have to be able to look at raw data and then apply statistical methodology of that. So a lot of the stuff I was doing was like chambers in a tool comparison across, wafers that were coming in over a fixed period of time. They came from wildly different input processing, like pathing through the factory. So when you break out, something by the time it hits the end of processing, you're at 500 something steps. Each of those steps have anywhere from usually like 3 to 50 different tools. And some of those tools have up to 12 chambers. So how do you sort through that data knowing that there's priors coming into that? And how do you like get the actual signal that you're looking for? But then not knowing which layer of this stack could have caused this defect or this processing abnormality. You have to go in and understand not just the data itself, but understand the processing that the data explains. So like, okay, what does this actually mean in this processing step? Like dry etch here, what can that actually affect? Okay, I can ignore all of that data or this signal that's popped up. You're not just looking for blind correlations. You're looking for correlations that imply something could happen. And then going to find the actual processing over a long period of history. And that also ties into what you said, Michael, like looking at distributions. That's all that data was. It's all continuous signal. So you need I had to build myself a little bit of a tool bag of statistical methodology in order to do that. Not everything was a simple t-test to compare these chambers. It's like, hang on a second. This is like a polynomial distribution here. And if I don't apply the right test, I can't even compare these chambers to one another. It'll just give me garbage data. So spending a lot of time with data, and then also what you alluded to as well, Deanna, which is understanding how your users are going to be interacting with this, like the product aspect of it. That's understanding for the corollary that I'm making right now about the actual semiconductor manufacturing process. So we all learned that in that stage early on when we were like starting up that department. We're like, how do we make sense of this and understand this? And a lot of it was, at first looking at CSVs, it's like, okay, I have this massive 4.5 gigabyte CSV file on my computer. And I'm just looking like row by row, chunking it and saying, okay, these 10,000 rows, let's plot that. What does it even look like? You're like, interesting. So yeah, it takes a lot of time, but I think it's required.
I think something that's nice about looking at the data, at least like for example, for someone who's just starting and maybe statistics is scary, you don't want to get into all that. If you look at the data, you don't have to have an understanding of statistics broadly. You just look at enough data points and your brain is already wired to identify patterns. You're already going to start building a mental model of how your system works, and you don't even have to do anything fancy to start to take insights from that. And I think that's really powerful too.
Yeah. I do think that the value proposition of statistics and distributions is that it shortcuts and it highlights specific types of things. But in theory, yeah, just looking at rows and columns of a data set can show a lot, especially from an edge case perspective. Just going row by row will show you some weird behavior. So yeah, diving in makes a lot of sense.
Mm-hmm.
And I feel like we're actually segueing really nicely to evals. So a few years ago, you joined Quotient. I'm curious, what is the value proposition of Quotient?
So Quotient has had some evolution over the years. Its value proposition has certainly changed over time. Latest, I guess, I don't know if you could call it a slogan or what, but our focus was on helping our users, build AI tooling, AI agents and understand how well those perform in a way that can automatically give them improvements without them having to devote time into that. So our goal was to go through their data, glean insights, understand, identify patterns, flag those to our users. So, hey, here are some specific types of user queries that are failing. Here are some specific failure types that we're seeing. And then on top of that, now that we've identified failure scenarios, we could then take those as a training set and train a small model to do what their GPT, whatever model is doing, better. And that was our value
Okay.
prop.
That makes sense. I am curious to go not deeper, but more high level. Evals, as we alluded to, is sort of arguably the most important aspect of Gen AI these days. Storing and managing context, a project that Ben is currently working and I was working on, is an absolutely essential piece. But alignment and knowing the AI is trustable and correct is sort of the big question. And as LLMs get smarter, they'll have more capabilities. But what if you're not specifying the task correctly? What if you're not specifying the right context? What if it gets a little bit confused and goes in a very different direction than you wanted it? So that's where evals comes in. So there's a lot of current structure for how to do evals properly. I'm curious, where is industry going to head? Because this is, again, such a big topic. Are we going to go more of a reinforcement angle? Are we going to always need a supervised set? Are we going to spend a lot of time on specifying loss functions? Like, what do you think are going to be the frontiers of focus for research?
So I think we're already in the reinforcement learning phase. I think we can all agree that having a supervised set is not necessarily, well, actually, I should take it back. I shouldn't say we can all agree, but I think in most scenarios, having a supervised set in AI systems is not really feasible. There is no single correct answer. There are many versions of correct answers you can supply that meet whatever criteria. And so supervised sets aren't the best way to learn or to teach behavior to a model, unless you are truly just looking for some simplistic, like this is the only way to get a correct answer. So reinforcement learning is just trying to capture, okay, well, there's some n-dimensional space of what good looks like, and I want to learn what that space is. So that's where we are now. I think the challenge with that is that it is already an eval problem. It's already okay, well, how do you even, like, as a human, if you cannot define what that space looks like, you cannot assume that a model is going to learn that. And so being able to set boundaries of will put you into good and this will put you into bad, that's the first challenge. And that's not even a LLM as a judge challenge. That's just a human sitting down and thinking about what is my criteria? What is my rubric? And that's already a hard problem. And then if you can do that, then building some framework to automatically make that assessment is the next big challenge. So I think that's like the immediate term direction of research, but thinking more forward, I think I see AI progression as kind of trying to mimic the human experience more and more. Every iteration has gone in that direction of like, okay, well, humans have some internal thought process, so let's give them reasoning ability. And humans aren't good at everything. They learn to specialize and they make use of tooling. So let's let models be able to recreate that. But then the big piece that is missing is that humans learn from their problems and learn from their mistakes, and that becomes encoded into their understanding of the world. And so that's, I think, where the next big leap is in AI, is being able to learn from your mistakes in a way that changes your understanding of the world as you progress and as you continue.
What does that look like?
Well, right now, MIT has been doing some really interesting research on like self-adapting LLMs that update their own weights over time. And so I think that's really exciting, and I want to see what comes out of that. But there's a long ways to go.
Yeah, the one thing that I'm holding out on, and this might be a really hot take, but epistemic honesty is, I think, the thing that LLM, like GenAI, is egregiously bad at. They're like the world's most confident liar. When they don't understand, there's no understanding. It's just based on the probability distribution of next token that is getting generated and the limitations of training data. You can ask something that is completely just without merit based in reality, and ask it in such a way that it is earnest and it doesn't come off as, satire. It will confidently answer something that is like violates the laws of physics. And when you like take a look at something that is so obnoxiously wrong in something that is provable, like, well, clearly there's not a way for us to reverse the polarity of gravity. Like, we all know that. But you can confidently get even like some pretty sophisticated models with, some prompt injection messing about. It'll start generating just nonsense. What does it do when you're asking it a business question that's like core to your company? It's like, hey, we trust this thing to make these automated decisions for us because, we didn't hire any more people in this department. And they're now doing something else, and now we have to supplement them with GenAI. That's where it starts to get real, I think, for people. And they're like, we need to be able to trust these things. So I think that any sort of future research that is applied to being able to have subsystems within GenAI services that will say, here's exactly how confident I am on the validity of this, and then give it to the users or the engineers who are building APIs to contact these services to say, yeah, let's not answer that, or let's provide a fallback or something, or just let the user know, like, this is not trustworthy. Like, we'll still give it to you, but don't really trust this. And Michael, what you're talking about with like context being added in as well, having an actual truthiness of a state of the world understanding that's updated through a temporal, configuration, where you can invalidate old facts or provide the relationship of truth, the truth of a system modifying itself over time, which is the state of reality. Having that as part of one of these systems as a tool calling functionality, and then layering on top of that sort of, here's how honest I'm being based on the facts that I know. That's when we start emulating real human reasoning of honest people. Right now, they're basically politicians, right? They will say whatever they can in order to meet their objective, which is make human happy. You're shaking your head, Michael. You're like, what?
So this has been such a big topic for me for the Databricks for Good project that I've been working on. I'm actually super curious to hear both of your guys' take at a high level. We take web scrape data, we transform it, we do information extraction, converting web scrape data into tabular structure. So now a blob becomes rows and columns of traits about a hospital. We then also do some unique ID creation, merge records that are the same ID, opting for something that is more recent or of higher quote unquote confidence. Then we expose that to an agent to do data science. The amount of freaking uncertainty introduced by this system is crazy. There's like 8 key steps where error can be introduced, and that compounds to a final conclusion that has such a wide confidence margin that it's really hard to know anything. So, Ben, you were talking a lot about how it will just confidently say something. And we also were talking about earlier how when we look to solve problems, we can go very hierarchically or do freeform association. The LLM sort of feels a little freeform these days, but you could apply a very rigorous problem-solving process with citations and other things like that so that each step in the logic chain is validated and correct. And there's infrastructure to do that, like tracing. I'm curious for both of you. Do you think LLMs will have this reasoning baked in, or are we going to have to always instruct an LLM to follow a 5-step process of look at the facts, hypothesize next direction, build a prototype, see if it works, then iterate continuously until we sort of reach a generally agreed upon optimum, sort of like a search algorithm like stochastic gradient descent. Or the LLMs actually have this reasoning built in a stable manner.
I don't know if Transformers architecture is ever going to support something like that. I think you're going to need like a multi-agent interface like that regardless. I think any of the services that we contact as like, oh, we're talking to this model, or talking to this service, you're talking to a lot of different models all at the same time with a lot of different instruction sets associated with them. So they're all pipelines. I think that the key to people that are using these systems is don't trust the hyper toddler who wants to just answer the question. Break it down to like restrict what it is exposed to, what it can and can't do. Don't give it like the 400 line prompt of like, hey, do all the things and like just give me the answer. These things are fantastically bad with those like massive prompt walls. But if you say, I want you to do this one thing, don't do anything else, just do this one thing. And then your system is the arbiter of truth around that. Where you're like, hey, while you're generating this thing, actually just give me, like the number doesn't actually mean anything really. You just tell it what a range to give and it'll generate something. But it's like directionally, like it's pretty confident. It's certain that it understands this. So it'll give like 94%. It's like, doesn't mean anything. It's just a high number on the range. But if it's like, I'm 8% sure that this is right, okay, maybe let's reject that one. If what it's generating is like, not so sure about this one. But your system that's behind that is controlling that's ingesting that and looking at that range saying, all right, that was garbage. Maybe we need to rephrase this question and then ask it again and have some sort of quality control loop built within the product that we're building. We can start approximating, getting closer to truthiness. As long as we inject clean context into the request, they're excellent at generating content off of summarized data. Like they're fantastic at that. It's just when you start asking a question with no context and say like, hey, just like straight vibes, man. Just like, give me the answer here. And you start reading through it. If you're the expert, you're going to read through that and you'll be like, we need to go run this by Deanna. We need an eval to check for this. But if you are just the user interfacing with the system and have no expert knowledge, you're going to get that response back and you'll be like, okay, cool. Sounds good. I can fill my car with diesel. Sweet.
Yeah. Speaking of running this by Deanna, I'm curious, Deanna, what's your take for these complex reasoning chains, for lack of a better word? How do you think about building evals for something like
Yeah. So first, just to like allude back to your prior question on, I think maybe hot take, but if you have a definable process where that can be generalized in a way, like anything that does not require an LLM, I don't think should use an LLM. And so if there is some kind of a step, or whether that's something mathematical or whatever, you should take that away from a model, write out a process that will do that, and then pass back results to a model. Models should, I don't think that they're not designed to be able to do logical reasoning, for example. They're designed to understand language and concepts. And so, yeah, that's my first take. And then as far as evaluating, like you've broken it out into all of these steps and processes, and they're all fitting together in some complex system. How do you know when things go wrong and where they go wrong and why they go wrong is a really hard problem. And the first step, if you have broken things out, taken things away from the LLM so that the model is only really doing one small piece of the puzzle, that makes your life a little bit easier, because now that you've got some predefined process that runs outside of the LLM, those are easy to check for. Those are your classic software engineering type tests. And so there's half of the job. The other half is figuring out for this like minute defined task that you've given your LLM, how do you know that that part happened well? How do you know that it interpreted the results it was given from your other process correctly? And I think you have to break it down into each of the pieces, have like some kind of an analysis on each of those steps, but also look at the whole. because it's easy to know that each step went well and yet still have like the wrong outcome in the end because the process wasn't right, or because, I don't know, maybe it took an inefficient detour, and you want to be able to capture that too. And so you have to look at the big picture, the full trace, and understand, well, was there something it could have done differently that's better? Good is not always good enough.
Yeah. Okay. Yeah. Lots of thoughts right now. How do you, just at a high level, how do you approach doing that though? Because there's so much complexity introduced. And also, Ben, I think you were alluding to a continuous score. Deanna, would you approach this in a sort of a continuous way where prior error compounds, where you have maybe a probability of confidence, or would you treat it more binary and compound that to make a continuous score? Because in the end, depending upon the question asked, ideally there's is it correct or is it not correct? And if it's incorrect, to what degree is it incorrect? So I think that's the target use case. But like, how do you even think about such a complex question?
Yeah, I mean, there's no single answer because it depends on what went wrong. It depends on how it went wrong. Like, is it a hallucination? If so, what type of hallucination? Did it get something slightly misworded, or did it just make something up? Those are very different failure scenarios that can compound in different ways. And if it's a small mistake, maybe a future step actually fixed it and resolved it, and like making those compounding errors is not necessarily the right way of going about it. So I think if you break it down into individual pieces, understanding for each given piece, given what it was provided with, like if, say, I don't know, you have a 3-step process, step 1 makes a mistake, step 2 acknowledges that there's a mistake and does something to resolve it, that's actually a good outcome. And so you don't want to penalize that. But you do want to understand, okay, well, given that step 2 works, step 1 is the place where I need to make some changes, address like whatever's going on in there. Or maybe it's okay for step 1 to have to make mistakes because it's a really complex reasoning task, and all you care about is the fact that step 2 is just able to identify the mistakes of step 1. And that's okay too. So that it's like there's no one right answer. There are so many different colors of what a good working system could look like, and it really comes down to you yourself having to create a definition of what good looks like and be able to measure not only what good looks like, but what it looks like for every step along the way as well. It's a lot of work. And I don't know if we're at a point right now that we can get around it without looking at the data.
I don't think you should get around it, even if there are automated systems. Yeah, it was a couple of weeks ago. I don't know if it was you, Michael, or maybe it was Owen or somebody who was like, "Hey, dude, the thing that you did to the email drafter, like, how did you do that? Like, how did you find out that you needed to make these architectural decisions?" I was like, I tried brute forcing something in such a stupid way by being lazy that I got to a point where I could no longer understand the system, and I didn't have any visibility into the stages. And I just did a work stoppage. And the first feature that I built was not, oh, I'm going to build a DAG or I'm going to build like task-based runners or whatever. It was, I need visibility into each stage of this pipeline. I need to see what the inputs are, what the outputs are, and I need it visible in the UI. And once I did that and just started looking at the data, I was like, there are conflicts in this prompt for this stage. Okay, now I need to like go and build like a prompt compiler with like reasoning, rules in it that will invalidate instructions that a user might pass in that goes against the system instructions. It was, how do I look at the entropy of that system by looking at the data output of each stage and saying, what constraints do I now need to put into the system in order to control this chaos? And once those started coming in, all of a sudden it became more stable. But I didn't just say like fire and forget on future features. It was every time I was iterating in the future, I was going into basically, okay, here's the 10 emails I'm going to use for testing. I'm going to look at the outputs of every stage of each of one of these before I write a single line of code, just to validate and be like, okay, things are stable. All right, make this one change. Now what changes in the stack? And it was exactly what you said, Deanna. It was like, okay, stage 4 changed in a way I wasn't expecting because I just changed stage 2. What the heck? Okay. First principles thinking. How do we go back and like make this not happen again? And once you have that visibility into the complex process, the iteration speed of doing those fixes accelerates to an insane degree. Went from making one feature change every 3 days on that abomination to, after the refactor, making 7 feature updates in a day because I was looking at the data. So I can't understate how important everything you said about that is.
I also, I think maybe kind of jumping from that to like another thought that popped into my head. A mistake I think we're making now is working with models in a way where we require them to be right all the time. I think the same way that humans are like, there will never be fully correct. There will never be, especially when we're putting them up to tasks that are ambiguous. And I think going forward, we're probably going to see more and more like designing structures that assume that they're going to make mistakes and have some kind of safeguards or ways to identify those mistakes. But like, yeah, I like to think of building AI systems less as get it so that it does things correctly and more like acknowledge that it's going to make mistakes and have some process that can capture those.
Yeah, that's a really good point.
Yeah. That's super, super interesting because you wouldn't ask a human to be right all the time. And then when a human makes a slight error, everything explodes. There are processes and guardrails that allow for errors. That's fascinating. I'm curious, do you think, or sorry, go ahead.
The challenge is that it's expensive. And so long as it costs money to do those things, I mean, it costs money for a human to do those things too. But I think that's the thing that's really slowing that directional change. But I think there will be a forcing function at some point.
That makes sense. Do you think anthropomorphizing AI is a successful development strategy? And Ben, I'm curious your take as well.
I mean, I give mine personalities.
Yeah.
Yeah. I feel like it's a double-edged sword. Because on the one hand, thinking of it as an imperfect being is a good way of approaching it. But at the same time, thinking of it as a being that can reason and that has logic and understands physical, tangible things in the way that humans do is also a mistake. I think that also leads to using AI and models in places where they should not be used, should not be applied. And I see that a lot. So I don't know. It's hard. There's no answer.
Yeah. There's definitely a trade-off, and I think people want to create mini versions of themselves that are just smarter and faster. So there's a lot
Yeah.
of emotion involved. And also because it's familiar, we're then able to reason about it better. Like when we define a desperation score in an LLM or like a reasoning structure or try to apply emotion basically on ones and zeros. It makes us able to think about it better, but it's different anatomy, so it operates differently. And it's also born out of different algorithms, not evolution, but reinforcement learning and optimization defined by a loss function that isn't exactly the same as reproductions. Yeah.
Yeah.
Triple-edged sword, in my opinion.
It's also like, especially working with Claude Code all the time, it finds my own mistakes, things like that. And it's really hard to work with something that's operating at that level and then remember at the same time that it's just at the end of the day predicting what is the next most probable token. And thinking of it that way always helps me like to take a step back and understand, well, the next most probable token maybe in like Claude Code in the coding world is a lot easier to identify than for this product that I'm trying to build. So that's always a good, healthy reminder that these things are flawed.
For the coding agents, I think they're fundamentally flawed. However, they really are good at following instructions and typing. But the moment you go fast and loose with, hey, I've got this feature, I need you to just build it for me real quick, or the worst that I've seen of like, hey, I just need this app that'll do like these 3 things. Could you just go and build it? And you go and look at what one of these things will create. It's like, cool demo. Good luck adding just 3 features to that without it just detonating in your hands. But if you take time and break it down to be like, all right, we're going to design a feature in this larger product, you have access to the entire product. And from that design, we're going to go and do a development iteration, of like, we're going to break this into 4 different phases. Each phase is 10 PRs. Let's block out together what each of these 10 PRs are going to do in order, and then correcting it over and over and over again until you have a plan that's like, this is fairly solid. This is kind of what I would build. And then when it's working on each of those like branches, putting stopping points in and reviewing constantly. It really is human in the loop, instantaneous feedback. That's how I use these things, and that's how we can ship code fairly quickly. But they cannot be trusted, because what they are doing is exactly as you said. Pick the next token based on all of the training data that it has from scraping public GitHub repos and Stack Overflow and other, other coding bulletin boards that are out there that are just full of garbage. And they're also reinforced through RLHF to get something locally correct as quickly as possible. So they're not going to go and build a solid foundation for a complex app unless you work with it to do that. They're going to build something that's like fast and loose, fastest thing you can get out there. And a lot of times that is some serious hot garbage that is just going to be a soup full of regret that you're going to be drinking.
Serious hot garbage, soup full of regret. That's one of the best ones I think you've done. It sounds terrible. Okay, well, Deanna, I had one final question for you. Do you have any advice to budding data scientists who want to learn more about evals or sort of take inspiration from your journey as focusing on getting into the data, just sort of as you have successfully navigated very impressive career? I'm curious if you have tips that would help others hopefully replicate or at least learn from your process.
I think the first thing that I would say is that not a single soul on the face of this planet has an answer. We do not know anything about evals. We don't know anything about AI or LLMs. There isn't a single researcher who can give you a correct answer because there isn't one. And so as someone who's starting in data science or AI, like that hopefully is very freeing to know that, I don't know, no one has the right answer. So it's okay for you not to either. And just approach things with a curious mind. And I think that's just so long as you are interested and curious about what outputs are coming out of this, that will lead you into the data. And once you're in the data, you're already most of the way there. That will get you a really good foundation and understanding of how LLMs work.
Heard? All right. Well, thank you so much for joining. This was a fascinating episode. I'll summarize some key takeaways. So, as Deanna just alluded to, being data minded is often a requirement for solutioning with data. And as we determined today, the undisputable truth is there's no shortcut. You just have to dive in and be curious. And actually, I would argue that is the shortcut, just going head first. Supervised sets are not super feasible to generate in the LLM GenAI world, and instead, humans setting boundaries should be the focus of what is good, what is bad, and what are the gradients of good and bad. If you cannot use an LLM, don't. LLMs are designed to understand language and not necessarily logic, and then get visibility into your errors that will really help you develop and choose directions for subsequent features. So, Deanna, if people want to learn more about you, reach out potentially, or more about Quotient AI, where should they go?
Yeah, absolutely. Please find me on LinkedIn, shoot me a message. Always happy to chat, whether it's evals, AI, life in general, always happy to talk.
Sounds good. Well, until next time, it's been Michael Burke. I'm my co-host.
Wilson,
And have a good day, everyone.
we'll catch you next time.